Hi, welcome to Dr. Vanderveen's AP Chemistry podcast. Tonight, our topic is limiting reagents. I have several objectives for this podcast. One is I want you to be able to identify when you have a limiting reactant or limiting reagent situation. I want you to be able to talk yourself through a strategy for solving these kinds of problems. And we're going to go through a complete problem at the appropriate level so that you've got a worked out model. All right. The key really to successfully completing these problems is to be able to recognize when you have a limiting reactant situation. Now, these are stoichiometry problems, and so the key here is really factor label. You've got to be able to do it. All right. But in terms of recognizing it, this is really the heart of the issue. If you are given information, mass information, for two, in some cases, even more reactants, then you've got a limiting reagent situation. And you need to know that. All right. Now, this information, instead of mass information, may include volume of gases to do these problems. Don't let that throw you. We can handle that. All right, let's talk about the general strategy for solving these problems. Now that we can identify them, we have to know what to do with that information. All right, you do want to make sure you know what you're solving for, including the units. All right, now the real core of this strategy is we're going to solve for the desired product, doing a factor label based on the amount of each reactant that we have information for. What this means is if we have two reactants that we were given mass information, we have to do two factor labels for that to figure out who the limiting reagent is. All right, we are making the assumption that everything reacts completely, so the reaction is going to completion. When we do the calculation, all right, whichever reactant gave us less product, whichever one gave us the smaller amount of product, that's our limiting reagent. All right, and that amount of product is the theoretical yield. All right, so the two calculations together give us the limiting reagent and the theoretical yield. Right, so we can talk about the strategy until the cows come home, but we really need to do a full problem, and that's really going to be the core of the rest of this podcast. So iron 2 oxide, FeO, can react with oxygen gas according to the following reaction to form iron 3 oxide, Fe2O3. Now in this particular reaction, there's only one product, so that simplifies things. All right, so let's pretend we have 10.8 liter sample of oxygen gas at 1.23 atmospheres and 175 degrees Celsius. Now, if you remember anything about gases, you might notice that we are not at standard conditions. This is not STP. All right, so we can deal with that. Don't worry. And we're going to combine that with 27.68 grams of iron 2 oxide. There are three tasks we need to accomplish, three parts to this question. Question A asks, how many moles of oxygen are available? We will do this using the ideal gas law, PV equals nRT. It's AP. They tend to bring in multiple concepts in one question, so it's not uncommon to find yourself needing to bring in the ideal gas law in what is really a stoichiometry problem. That's okay. We can do that. Part B asks, what's the limiting reagent? All right, identify that limiting reagent, back up your answer. All right, with calculations, you can't just blindly state it. If you guess or just write it down and don't show how you got there, you're not going to get credit. And finally, What's our theoretical yield? How many moles of product are formed? In this particular reaction, there's only one product. So that simplifies our decision making. Let's talk about a general plan. Anytime you're doing a stoichiometry problem of any type, start with a balanced equation, got that. We need to calculate our molar masses. Get your periodic table out if you don't have it already. All right, you want to make sure your molar masses have more precision than you need. Our answer needs 3 sig figs if you go back and look at the problem. So I've recorded all my molar masses to at least 2 decimal places. All right, so the iron 2 oxide is 71.85 grams per mole. The diatomic oxygen is 32 grams per mole. The iron 3 oxide is 159.70 grams per mole. No problem. I should mention at this point, if you don't already have your green equation sheet, your formula reference sheet, and your calculator handy, go get them, because you really won't be able to go too much farther without them now. All right. What we're going to do is use the ideal gas law. Remember, PV equals nRT, and we'll use that to solve for the moles of oxygen. All right. From there, once we're done with that, we'll use our stoichiometry technique to find the limiting reagent and find that theoretical yield of moles of product by doing 2 factor label calculations. All right, so let's go through part A. We're going to use the ideal gas law. All right, PV equals nRT. If you haven't memorized it yet, I do it right away. Don't wait. All right. If you've forgotten parts of the ideal gas law, you might remember that R is the universal gas constant. All right, and it is known, it's a given, and I don't have as much precision here in its value when I type this up, so we're going to add a little 1 here. Its value is 0.0821 liters times atmospheres per mole per Kelvin. It's on your green sheet. Don't worry about memorizing it, although quite frankly you use it so often that you may find yourself knowing it without even trying. The other thing is that our temperature needs to be in Kelvin. If we are given our temperature in Celsius, so we have to add 273 to that to get to Kelvin. So when we go ahead and do that, we were given a temperature of 175. 175 plus 273 comes out to a temperature of 448 Kelvin, which we have to use in the equation. Have to be in Kelvin. We're going to rearrange the ideal gas law to solve for moles. Some nice simple algebra there. All right, and then it's time to substitute and evaluate. We want to solve for moles. We were given the pressure as 1.23 atmospheres. We are given the volume as 10.8 liters. The R value is 0.0821. I'm not putting in all those units. I know I should, but it's too hard to write with this pen. And the temperature in Kelvin we just calculated as being 448 Kelvin. So we go ahead, we get out our calculators, we plug everything in, and we get 0.361 moles of oxygen. Great. Part 1 done, 2 done. 2 more to go. Parts B and C we're going to do together. We're going to set them up as factor labels. We're going to solve for the moles of product based on the amounts of each reactant that we were given. We're going to calculate that out. Whoever gives us the smaller number, that'll be the answer that we want. All right, so we have moles of oxygen. We know from the balanced equation that for every 1 mole of oxygen that reacted, that 2 moles of product form. All right, and so we just need to calculate simple multiplication here. We get an answer of 0.72. That's supposed to be a 2 moles of Fe2O3. All right, but that's not enough. We can't know if this is the limiting reagent or not until we've done the second calculation. We really do have to compare them. So we're going to set this up. This will be a two-step calculation, as it turns out, because we're solving for moles of Fe2O3. We know that for every 71.85 grams of FeO, that's equivalent to 1 mole of FeO. We also know from the balanced equation that for every 4 moles of FeO, that 2 moles of Fe2O3 form. And so we calculate this out, we get our calculator, we punch everything in, and we get an answer of 0.193 moles of Fe2O3. Well, it's quite clear from comparing the two calculations that 0.193 is smaller than 0.722. And therefore, we can conclude, therefore, all right, the limiting reagent is the FeO, and the theoretical yield is 0.193 moles of Fe2O3 form. I hope you found this podcast to be helpful, and I'll see you next time.